Alright, so what we're covering here is in chapter 7.3 is multivariable linear systems. And so we're talking about three variable systems of equation and some dealing with three variables. So it might not always be square, but we'll look at that here in a little bit. Now the first thing we're looking at is row echelon form. Now row echelon form is really saying that it's increasing kind of a stair step, we'll look at it, and back substituting. Now, the method of elimination can be applied to a system of linear equations in more than two variables. In fact, this method easily adapts to computer use for solving linear systems and dozens of variations, and we'll see some of the calculator approaches to solving this. Now, what row echelon form is taking a system of equation, a three-variable system of equation, and having it in this stair-step form, where x, y, and z, so x is by itself, y is by itself with no x in front of it, and z is by itself. So we have this step-down form. And once we get it in this form, we can solve. So this here is row echelon form. Now for what we start doing when we start solving the equation from here, we're not going to use row echelon form. We're going to use something called reduced row echelon form. And reduced row echelon form will get it in the form of x, y, z by themselves. We don't have the other variables in there. So, row echelon form gives us this stair-step pattern. And once we get it in this form, we can go about solving it. Now, solving it from here is pretty easy because, well, one thing, they gave us z. Z is 2. And what I can do is I can plug this into the one above it. So we can say that y plus 3z is equal to 5. So I'll plug 2 back in. So I get y plus 3 times 2 is equal to 5. Well, 3 times 2 is 6, so I get y plus 6 is equal to 5. And at this point here, we can subtract 6 from both sides. And we subtract 6 from both sides, we get that y is equal to negative 1. So in our solution, we don't have x, but we have that y is negative 1 and z is 2. And last but not least, to find x, well, I can take the top equation, x minus 2y plus 3z equals 9. Well, we already know y and z, so we have x minus 2 times negative 1 plus 3 times 2 is equal to 9. Well, negative 2 times negative 1 is plus 2. 3 times 2 is 6 equals 9. 2 plus 6 is 8. And last but not least, we can subtract 8 from both sides. And when we subtract 8 from both sides, we get that x is equal to 1. And we get the solution for this first problem here as 1, negative 1, 2. And that's all we have to do for this one here. And we just ended up plugging one variable, so z, back into this one, solve for y. Then plugged y and z into the top one and solved for x and got our solution. Now, looking at this here, so as I said, so they plugged in 2 and found y. Plugged both of them back in the first one, and we got our order triplet. That's all we have to do for this here. So we'll do another one here. I'll do one more with you. So we found z. So x, y, z. Well, z is negative 1. Now we could plug negative 1 here in, and we get y minus negative 1 equals 8. Well, negative and negative make a positive, so we have y plus 1 is equal to 8. Subtract 1 from both sides, and we get y is equal to 7. And last but not least, to find x, we'll plug in x and y. So we have x minus 2 times 7 plus 2 times negative 1 is equal to 20. So negative 2 times 7 is negative 14. 2 times negative 1 is negative 2 is equal to 20. 14 minus 2 is negative 16 is equal to 20. We can add 16 to both sides. And we get x is equal to 36. So our solution for this one here is 36, 7, negative 1. And that's all we have to do for this problem here. So what we're looking at next is Gaussian elimination. Now, Gaussian elimination is kind of a set of procedures or steps involving adding or subtracting rows from each other. So we can interchange two equations. We can multiply one of the equations by a non-constant 0 and add or subtract to the others. And really what it's talking about is we're using these equations to get into a row echelon form, kind of like how we just saw with our equations before these here, getting it into this form here, where we have this stair step. So we can do that by adding or subtracting them from each other. And so really we're wanting to get it so that y is by itself, so on and so forth. But I wouldn't worry too much about doing this here. I would just go on and solve it. Now, I'm going to show you using this one here how we can use the calculator to solve these. So we're going to take our equation here. Now at this point here, if you want to make sure you have it written down somewhere, you can. Because what we're going to do is we're going to use matrices. We're going to solve this by using a matrix. And how we're going to do that is I'm going to write it in an augmented form. And the augmented form for this matrix is going to be 3, -2, -1, 1, -1, 0. And kind of this line here. So really I'm just grabbing the coefficients, the numbers in front of the variables, and putting them in this form here. And what we'll do is we'll take the calculator. So you'll take your graphing calculator, we'll plug this in to solve for this here. So when I get my calculator out here, so I'm going to clear this out. Now what we're going to do is we're going to hit second x to the -1, which will bring up our matrix. And we can go over to edit, and we're going to put this in the first matrix. Now our matrix is a 2 by 3. We have 2 rows and 3 columns, and we'll plug our information in. So 3, and then -2, -1, 1, -1, and 0. And this is our matrix here. And at this point here, we can do second quit. Then we're going to do second matrix. And this time, we're going to go over to the second one. And we're going to go down. So scrolling on down, this matrix. And I'm going to go to RREF, Reduce Row Echelon Form. Now this REF, Reduce Echelon Form, will give us our stair step appearance. But I want Reduce Row Echelon Form because it's going to be easier to work with. And once we hit enter on that, we're going to go back second matrix and then put A in here. And once we hit enter, it will give us this here. So 1, 0, -1, 0, 1, -1. And that's our answers. So once we did our reduced echelon form, we got 1, 0, 0, 1. And I've already forgotten. -1 and -1. So we got -1 and -1. Now if we think back to how we set this up, well, we set x in the first spot, y in the second. So what this is saying here, our first equation is that x equals -1. Here we have y equals -1. And this is our simplified row echelon form. So it tells me that our solution for this here is -1, -1, x and y. And that's it. Now, it's possible to solve this using a row operation or row operations to solve this here. Now, it's not that it's not important to know this, it is helpful, but as long as you have a calculator, you don't really need to do it. Now, if you want to see how it's worked, it is worked out on page 491. I just don't see a big enough importance or it being really important enough to go on and work this one out when we can do it this way, or we can do it by elimination or substitution. Now, we can do the same thing here. We could use row operations and manipulate it so that we get it down into a stair step case where we have x by itself, y by itself, and z, and all of this here is blank. Or we can use the calculator like we just did. Now, the way that we'll do that here is we're going to write a matrix. And the way we write the matrix is that we're going to grab all of the constant numbers. So here, from x, we'll get 1, then we'll get -2, 3, x, y, z. And we always want it in x, y, z form. And then our fourth number would be 9. Here we're going to get negative 1. 3, because there's no z, we'll put it in as 0. Then negative 4. Here we're going to get 2, negative 5, 5, and 17. Now at this point here, we can type this into the calculator. Now I'm going to write it down just so I have it. 1, negative 2, 3, 9, negative 1, 3, 0, 4, 2, negative 5, 5, 17. So when we pull our calculator up, so for this here, I'm going to go second matrix and go over to edit because I want to edit this matrix. Now this one here, we're going to have a 3 by 4. So whenever we deal with a 3-variable system of equation, a squared 3-variable system equation, our matrix C will be a 3 by 4. And we can go on and input our number. So 1, negative 2, 3, and then we have 9. Then we have negative 1, 3, 0. I put a negative on accident, but that's fine. Negative 4, 2, negative 5, 5, 17. And we have this here. Now our next step in this process, we're going to go second quit. Now a cheat that we can use, because we have our REF here and we inputted that matrix in A, I can scroll back up to it, hit enter, enter, and it'll give me this here. So we have our diagonals of 1 saying that x is equal to 1, y is equal to negative 1, and 1 is equal to 2. And that's all we have to do for this here. So this here, this matrix, ended up reducing to 1, negative 1, 2. And over here we got our 1, 0, 0, 0, 1, 0, and 0, 0, 1. Which told me that the solution for this is 1, negative 1, 2. And this will work for any 3-variable or 2-variable system of equation. We can do it with any of them. And the 3-variable systems of equations, I'm more inclined to do this here because it's a lot easier to do it than to solve it out. Because here's the way that we would end up solving this. We would look at this here because the leading coefficient of the first equation is 1 by keeping the x in the upper left position and eliminate the other x terms from the first column is what we'll do first. So that we'll write the first equation, write the second, and add the first to the second so that the second equation loses that x. So that we get this here. Now, adding the first equation to the second gave us this new middle equation. Then what we're going to do is we're going to multiply the first equation by negative 2 and add it to the third equation so that that x variable cancels out. And what we're left with is negative y minus z is equal to negative 1 for our third equation. Now what we want to do is we need to eliminate the y out of the third equation. And we'll do that by adding the second equation to it, which ends up giving us this here, this row epsilon form. But last but not least, we need to multiply the last one by 1/2 so that z is by itself. And then we can solve back through. Now hopefully looking through this here, we would do that and we get the same answer. But it's a little bit easier to just use the calculator than this here. The row epsilon form is nice. It's helpful in some ways, but it is a process to go through. Now with a system of linear equations and 2 variables, the solution of a system of linear equations of more than 2 variables must fall in one of 3 categories. There exists exactly one, there exists infinitely many, or there's no solution. And this is kind of a visual representation of it. Now here we have a solution of 1 point, so there is exactly one solution. Here, the solution is one line, so it's the equation that makes up that line. And that's kind of our infinitely many solutions. When we talk about a system of 3 variables having infinitely many solutions, we're talking about that equation of the line. The equation that represents that line, any point on that line would be true. So that's infinitely many. That's our infinitely many case. Here, we have only one plane, so the solution is one plane. It's all the points on this plane because all 3 planes are the same. So all the points on that plane are the solution. Here, none of the 3 planes intersect at the same spot, so there's no solution, as well as this one here. Now at this point in Algebra 2, we talked about, okay, well there's infinitely many because the bottom equation, it worked out, and we just said that the solution for this is infinitely many. Now here, on the infinitely many solutions, we're going to have to find the equations that represent that. Actually, let's look at a case where it is infinitely many before we move on. So we're going to look at a case where there are infinitely many solutions. So x minus y plus 2z is equal to 5. Negative x plus 3y minus z is equal to negative 2. And 2x minus 4y plus 3z equals 7. So this one here, we already know it has infinitely many solutions. Now what I'm going to do is I'm going to do our augmenting matrix. I'm going to use this matrices to solve this. And so we're going to solve this by a matrices. So how we solve it is we're going to take the numerators. So here we'd have 1, negative 1, 2, 5. Then we'll have negative 1, 3, negative 1, negative 2, and 2, negative 4, 3, and 7. So we have these numbers here, and we're going to use them in our matrix. So at this point here, you can go on and grab your graphing calculator and go on and start plugging them in. And so I'm going to do that now too. So I'm going to pull up my graphing calculator. And we're going to go second matrix. So we went second matrix and we scrolled over to edit. Now we still have a 3 by 4, but this time we have negative 1, well not negative, we just have 1. Our next one is negative 1, 2, 5, and then we have negative 1, 3, negative 1, negative 2, 2, negative 4, 3, and 7. And once we get the matrix plugged into the calculator, we can do second quit. Now again, I already have RREF typed in here, so I could hit enter and bring it back down. But if you don't have it in there, we can do second matrix. Go over to math and either scroll up or down to RREF, hit enter, and then we need to get the matrix, so we'll do second matrix, enter, enter, and we get this here. Now if you notice something's a little bit different with this one here is that we don't have zeros in these spots here. And the last row is all zeros. Now when we covered this before in Algebra 1, we said that having the bottom row of a matrix C, having all zeros meant that this is a infinitely many solutions. Because if the bottom is all zeros, it's infinitely many. Now if the bottom had 0, 0, 0 and then a number in this last spot, it was no solution. It was a no solution because there was no values that would work for that one there. Now this one here is infinitely many because the bottom row is all zeros. Now we're going to go back to here and I'm going to put that down. So our matrix that we got was 1, 0, 2.5, 6.5, 0, 1.5, 1.5, and then we got all zeros. Then we got all zeros in the denominator. Now what that tells me here is because all zeros in the denominator, I'm going to set z equal to a. We're just going to pick a value. Now in most throughout this book, they're going to use a as just a variable, a number that we plug in. And what we'll do with that there is now, when we look at the other equations, well, the top one is written, because this is x, this is y, and this is z, would be x plus, well, there's no y value, but we do have 2.5 z is equal to 6.5. Now the other equation, we didn't have an x, but we have y plus 0.5 z is equal to 1.5. And then we don't have an equation with z because there's really nothing down here at the bottom. It's only in these two here. So this is kind of why we set z equal to a. Now at this point here, I'm going to plug a as z into these two equations. So here we get x plus 2.5a equals 6.5. And at this point here, I'm going to solve for x. So I'm going to subtract 2.5 from both sides. And again, this seems weird and it's fine. Just stay with me. And what we get is x is equal to negative 2.5a plus 6.5. We'll do the same thing with y in here. So what I'm going to do first is plug in a for z. So I get 0.5a equals 1.5. Solve for y, so I'm going to subtract 0.5a from both sides. And I get y is equal to negative 0.5a plus 1.5. And really what we're saying is that z can be any value, because since it became zeros, it can be any value. And x and y are in relationship to each other with z, because whatever value z is, it will reflect what x and y can be. So since we set z equals a, we now have two equations here that reflect how x and y change according to what the value of z is. And that gives us an ordered pair. It gives us negative 2.5a plus 6.5, comma, negative 0.5a plus 1.5, comma, a. And this here is our ordered solution for these three here. And it works out that any value of a that we plugged in will give us a triplet, an ordered triplet, that will be a solution for these three equations here that will work for all three. And that's all we have to do for this here. Now in Algebra 2, when we cover this, we just said, hey, bottom row is all zero, so it's all real solutions. But it's not just that, it's these equations here give us the solutions that will work. So what we do with this here is we set it up, find out, so here's z is equal to a. We plugged it back in and we got our numbers here. Now this really comes into play especially when we have non-square systems of equations. And what that's talking about is I have two equations with three variables. Now we can still use a calculator to do this here, and I would suggest using a calculator for this. So we'll set up a matrix. So I'm going to still grab the coefficients. So 1, negative 2, 1, 2, 2, negative 1, negative 1, 1. And we would have this here. So it still works the exact same way we did with the other ones. So 1, negative 2, 1, 2, 2, negative 1, negative 1, 1. Now at this point here, I'm going to pull the calculator up again. And what we're going to do is we're going to go back into the matrix. So second matrix. And go over to edit for matrix A. Now this time we have a 2 by 4. So we have 1, negative 2, 1, 2, 2, negative 1, negative 1, 1. And now that we have this typed in, again, we're going to go second quit to come back here. And I'm going to go up and use the REF that we already have and hit enter, and it will give me this augmented matrix. And we're going to use that here in a minute. So let's go back to our page here. So the matrix that they gave us when we simplified it here was 1, 0, negative 1, 0, and 0, 1, negative 1, negative 1. So again, we have x, y, z, and then what it's equal to. Now the top row tells me that I have x minus z equals 0. And the bottom row, well, I don't have an x, but I have y minus z equals negative 1. So here I have two equations in the form of z. or x minus z equals 0 and y minus z equals -1. So here, we ended up getting two equations both in terms of z, and because they're both in terms of z, I'm going to set z is equal to a, because x and y are dependent on z. Z is not dependent on any number, so we'll set z is equal to a. So that means for this one over here, we have x minus a, when we plug it back in, is equal to 0. I can add a to both sides. So it means x is also a. And when I plug it in here, we get y minus a equals -1. I add a to both sides, so I get y is equal to a minus 1. So our solution for this is a, comma, a minus 1, and a. And any numbers that we plug in for a will work for this here. And we could try setting a equal to 1. So that would mean our solution is 1. 1 minus 0, 1 is 0, comma 1. So 1, 0, 1. So let's look at this here, 1, 0, 1, for this here, for this solution. Now I'm going to erase everything else. We're going to keep these here and move these back up. So this was our solution, a minus 1, and a, and we let a equal 1, which gave us this solution, these numbers here. And if we plug it back in, so 1 minus 2 times 0 plus 1 equals 2 will work. Well, 2 times 0 is 0. Well, 1 minus 0 plus 1 is 2, so that worked for that one. So let's try it for the bottom equation. So that'd be 2 times 1 minus 0 minus 1 is equal to 1. Well, 2 times 1 is 2. Minus 0 minus 1 is equal to 1, so it worked. And it'll work out for any sets of numbers that we plug in for a will give us a true solution. Now here they went through the other method, and we get this here. And it cannot be unique, but we could try any of these here, and we would get a solution that works for any of these ordered pairs. Now we can do one more here. Let's do another one. So when we look at this here, again, we're going to write our matrix. That's the first thing I'm going to write. And our matrix for this here is going to be 1, -1, 4, 3. And on bottom, we're going to have 4, 0, -1, 0. Just because we don't have a y term, that's fine. We just put a 0 in place for that term. And now, we're going to go over to the calculator. So I'll bring my calculator back up. And again, so here we're going to go second matrix and go over to edit, and we're going to edit matrix A. It is still a 2 by 4. Now our first number is going to be 1. Our next number is going to be -1. Our third number is 4. And the last number on the top row is 3. Then we're going to have 4, 0, -1, 0. And these are our numbers that we're going to input here for this system. And we'll do second quit. And then we're going to do our REF for matrix A for our new matrix. And we're going to get this here. Now we get these decimal numbers which aren't as nice to look at, or not as easy looking or kind of easy to work with, but that's fine. We can have decimal numbers. There's nothing wrong with that. And now that we have that, we're going to go back to our other page. So the matrix that we got was 1, 0, -0.25, 0, 0, 1, -4.25, -3. And again, our two equations we got from it is x minus 0.25z equals 0, and y minus 4.25z equals -3. So again, in both cases here, in both of these here, we are given two equations that are in terms of x and z, y and z. So that means for me is I'm going to set z is equal to a, just a number. And what we can do is we can plug it back in for both of these here. So x minus 0.25a equals 0. Then we would add it to both sides, so we get that z is equal to 0.25a. Here we get y minus 4.25a equals negative 3. We would add 4.25 to both sides, giving us y is equal to 4.25a minus 3. So our final solution for this is 0.25a, comma 4.25a minus 3, comma a. And that's it for chapter 7.3. That's all we're going to do for this year.